Good afternoon, everybody. I'm so happy and excited to be here for the next 3 days. I looked into the agenda. It seems really, really awesome. My name is Zvonimir. I got my bachelor's in electrical engineering in Belgrade, taught analog electronics there for a while during the school. Went to Caltech, got the PhD in high-speed gallium arsenide electronics, high-voltage gallium nitride devices. Went to IBM Research and stay there. I'm still my first job. It's IBM and Hitachi making joint venture, Hitachi Global Storage Technology that became AGST that got acquired by Western Digital. I sit in the lab until 2008 and then kind of started running the architecture group. So the presentation and what we do in Western Digital covers kind of several things. We do, in my department, have a RISC-V core design group focused on the RTL design of our first and follow-up RISC-V cores. We have a software toolchain development group also focusing on RISC-V embedded. And then on the research side of things, I have a memory controller group focused on a new generation of controllers that have ultra-low latency, error correction, and wear leveling management for new types of memories like phase change memory. And I also have a prototyping group that's focusing on some of the designs that I'll show today, and it's also focusing on machine learning accelerators, which I will not show today, but we'll be happy to chat in any kind of break and dinner, etc. So presentation today is about RISC-V CPU project in WD from embedded cores, meaning from something very practical today, to a vision of data center processors with open interfaces, which is something strategically very important for kind of creating a better enterprise data center market in the future. All right, blah, 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 blah. So, you know, I'm always, never mind, I'm on the tape. Agenda. I think you guys know this. I'm going to run super fast through the RISC-V Instruction Set Architecture. I think you had Krista here presented. And so I'll run through that quickly. Maybe I'll say a few things what were important to me in my project, what was unique for WD. Then I'll go into Western Digital first core. I'll show a microarchitecture introduction and show you some performance benchmarks that I think you'll be kind of curious to see. And then I'll transition to this enterprise data center RISC-V CPU vision. Right, so this first part has a kind of nice explanation of the architecture and data. The second part, I really looked into different kind of papers and results we published over the last 2 years, so I make sure it's justified with some actual measurements as opposed to being a marketing vision, which it sort of is, but it's all real stuff happening in the lab. And then I'll talk about planned open source contributions. And in my backup, I also included a couple of our charts related to open source hardware licensing, which is the topic that fascinates me, and I have inspired some lawyers in Western Digital to kind of get involved in this as well. So what's different about RISC-V? You guys all know it's a RISC-based architecture. It's quite small, so it's relatively easy to implement a RISC-V compliant core. Has a good separation between, because it was relatively new and designed like 5 years ago, there's a good clean separation between the user space and privilege ISA for running in a modern secure OS. And it attempts to avoid microarchitecture or technology-dependent features. And from that perspective, we give it an endorsement. We believe this is a true statement. And it's very modular, allowing with a lot of code space for both standardizing very useful things like debug, port implementation, trace, vector set instructions. And there's also a private code space that's interesting for proprietary things. Like, for example, for us, if you wanted to implement some instructions that are uniquely designed for managing a NAND component channel, and it's not necessarily interesting to the whole world, and it's interesting to us to keep keep it proprietary. So there is a code space for that. And I'm also learning in the new markets, in the new expansion markets for RISC-V, like China, India. It's actually also very nice that there is that proprietary code space that can be used for market unique extensions while keeping the core part compliant, so that we can, we can all run the same software. So RISC-V for embedded and IoT applications. What are the key requirements? Oh, here it is. I was trying to figure out where I can see the slides, so I don't have to keep looking at the screen. So the key requirements for IoT is usually some kind of very specific balance between the performance and power. So people want to tune things for their applications, like a NAND controller. They want to establish very commonly some new software hardware boundary, meaning there is added instructions or there is simply hardware engines, like in case of NAND controllers, there is a very low latency, or at least according to the media, low latency error correction code engine. This is a kind of hardware that you do not want running in a firmware. It would take too long. It would potentially take milliseconds, right? So you have a dedicated hardware. And then there's a issue how you manage it through some memory map registers or with new instructions, etc. So there's new boundary. There's a requirement on performance, how you're executing your firmware, and there is a requirement for power. And the attractiveness of RISC-V is this freedom that you're maybe starting from some existing open source core or starting fresh. But because you're owning microarchitecture, you can tune this freedom very nicely according to the application. And in addition, you have a freedom to implement custom instructions. So in the past, in all of our designs, every time we had a hardware accelerator, it was always done through a memory map registers, through the inline assembly that was actually used, how to manage them. So in many cases, we kind of did it the way we could to kind of avoid NRE projects. But with RISC-V, there's like a whole new way of looking at things to try to make them more elegant, more elegantly integrated in software tool chains. And yeah, one of the challenges is knowing what's forward and what's backward. Yeah, for power, usually you will. It's not unusual to expect. Like in 28 nanometer, to expect 0.05 millimeter square sizes for the core. It's not unusual to have a milliwatt measured power requirements, etc. The challenges with closed architectures is that usually you're facing a third-party IP provider that has a fixed array of cores, and you can pick from that vendor what you want, but you don't have fine granularity of choice. Sometimes you have an application where it's really embedded. It only really runs integer arithmetic stuff, but it's coming with a floating point unit that's kind of black silicon and the whole thing, and it cannot be removed. So this actually happened. So that's one of the challenges. The implementation of accelerators and added instructions in that world also leads to a leakage of use cases. And through the leakage of use cases, your customers, your relationships, your business is kind of leaking out of the world. So this is kind of interesting, and I'm being forthcoming and honest with it. It's a case where open source architectures enable you to share what's great for sharing, and those things that are really proprietary, like what's your customer and what's your IP, you can keep that proprietary. And this is only possible, in the open world. So what were the Western Digital key requirements when I started this project about, so in Western Digital, we have been working on open source ideas for processors for a while. But when we got our new CTO, Martin Fink, we got a really strong hardware accelerator for all these projects. So suddenly I find myself in the position, I have the real RTL team, and I'm developing core internally. And if you look what the key requirements are, it's improved performance, reduced power, so people want better performance, less power, as expected. Enable some things that are really interesting, like tightly coupled memories enablement. take advantage of open source software support. So this is actually really nice, having a opportunity to develop a software toolchain that's based on open source software is really, really nice. And it gives you that that goes straight, that open source software support goes straight into this bottom thing, which is not all the cores need to be open source. Not all the cores need to be developed in the house. It's just okay to have like some license, some in the house, some from open source world, and you can go back and forth. You can keep your tool chain. And then that's kind of a really nice value add. Because normally before you would pick an architecture, and through the software toolchain that you develop in-house and tune it for your development, you totally get locked into one architecture. So the nice thing about RISC-V, you lock yourself into RISC-V, but there is going to be actually many more options in the marketplace in that spectrum, from academic core and open source core, licensed core, etc. What else? And yes, then again, nice thing on the requirements that RISC-V enables, implementing internal buses, and for which pre-existing IP exists, like think of the ECC engine, and then enable adding proprietary and future standard instructions. So I'll go a little bit more detail now about our core. And I think the first core that we have developed, and we'll get it by December, will have a name. So now it's going generic, and we're looking for a name that we can use. What is it? I'll have a block diagram with more detail, but just to get us started, it's a two-way super-scalar, mostly in-order core with 9 stages pipeline, or maybe 8 stages plus write-back, whichever way you want to count it. We support RV32 IMC, which stands for integer, multiply, divide, and compressed. And we have 1 load store pipe, 1 multiply engine, 1 divider, and 4 ALU engines. And performance targets that we were given were Drystone better than 2 MIPS per megahertz, and CoreMark better than 4 CoreMarks per megahertz, and the capability to do 1 gigahertz operation. The designing of the core for the very experienced team that I have, with a lot of smart people who came from mostly Oracle Sun background, the core part was fun and exciting thing to do. The Encore was a lot of work, because Encore is really implementing the hardware interfaces like buses, debug and trace, platform interrupt controller that had to be defined and negotiated by somebody developing a documentation of what's being implemented. So this Encore part, even on a relatively simple core, is like what generates tremendous amount of work and meetings and discussions to understand what it really is. And here is the little bit more detailed block diagram for So this is way above my level. I can design a 2-stage core. This is what I've done in a class, and I did really well, like 99. But like if I look at my own group designs, I can I'm not as good. But we have, what are the interesting features? So it's a 9-stage pipeline. We only have 4 stall points when we will stall the core. When we fetch, we have the aligner units that really is important to us to handle compressed instructions. And I can talk about compressed instructions before. And after we decode, we have 2 pipes. Ergo, it's a super-scalar core. And as you progress through the pipes, we have 4 ALU engines that are located at EX1 and EX4 in both I0 and I1 pipe. And then we have single load store pipe. We have 2 cycle latency multiply and 34 cycle out of pipe divider synthesized. Everything here is synthesized, there's no custom. The interesting feature, depending on what you have seen before about this design, is you can do your arithmetic operation either at EX1 or at later stage in the commit. And meaning if you miss something, like you have a load that will give you a result with two cycle latency, you can actually do it later in the pipe and improve the throughput. So this design, in random code gives you 2x acceleration, but in realistic code it will give you like 35, 40% in terms of instruction per cycle acceleration. Yeah, so those are kind of the key features. One of the things that is very important for the performance is obviously how you do the branch prediction. So in the embedded design, and so I obviously from the computer architecture classes, we learn BTB. You also learn G-share, and maybe at the end there'll be some fancier scheme using DEC alpha, like a tournament predictor, etc. So in embedded projects, you will kind of stop at G-share. Normally, you would go for the G-share because it gives the best balance in terms of size and what it can do with realistic code, meaning it can get you into sort of a 94-95% range, depending on the size of the registry. And this is where the Cormark score changes. So if you go with a 2048 entries in the BTB table, you can get really nice Cormark results, but you will also consume a lot of your area. So that's kind of a tuning parameter, what's really needed for the application, what kind of firmware application is running, etc. In terms of the sizes and the physical design, our target technology in this case is 28 nanometer TSMC. In the core can reach frequency target to 1 gigahertz, actually currently more around like 970 megahertz, but very close to a gigahertz. Obviously in the different corners of the technology, we get different areas. So in a worse corner, for 1 gigahertz operation, will consume about 0.15 millimeters square. In a good corner, to get to 1 gigahertz, we consume 0.09 millimeters square. So that's the current sizing. I labeled, actually on this diagram, the guy who did the physical design, he actually labeled in this chart, which country is which part of the design. But this, actually, Lawrence had a lot of problems with it. And then 7 days ago, I actually memorized, and I realized now I haven't checked yesterday again, so I forgot. I only remember that this is the branch prediction, but I forgot what's the rest. If you ask me, I can tell you if it matters to anybody. Apparently, there's a lot of IP on how you do the placement in physical design, so it's not kosher to talk about it. Performance. This is the exciting part, and something went wrong with this chart. I don't know why this happened. Like every other entry on the x-axis is missing. Okay, so the second bar is Western Digital Core, so the WD core is currently at 4.9 Cormark per megahertz, with the caveat that result is obtained with using 2048 BDB entry for the branch prediction. So so you get like kind of nice, and it's a currently very nice result. So this is basically what we are validating through the RTL simulation, and it's a very nice result. It's ahead of many other cores that are quite bigger. It's we've been able to get additional performance gain, like about 4.9, by experimenting with compiler. And we are hiring some compiler people, and we hope to kind of, we'll see whether these optimizations that are working for us in the lab, whether that's something that can be upstream and accepted. But if it does, it can push these things to 5.1 kind of territory, which is kind of really nice result as it comes to core mark.
Which compiler are you using, GCC or CMark?
GCC. And in our software toolchain group, we definitely are very interested in CLang. We started talking with different people in the industry. We would want to see improvements in the CLang, and we want to contribute to the improvements in CLang so that maybe we can transition to CLang. And one of the reasons why I didn't put it in the chart, but I'm happy to talk about it because we kept these conversations very much in open, is a efficiency of the current glibc and CLang in generating a good code density and using RISC-V compressed instructions, etc. So there's some issues there that require work and improvements. For those, I think probably all of you are familiar, but CoreMark is a benchmark that's always renormalized to a single execution context, and that's always renormalized to the frequency, right? So that's why you sometimes can see confusing result. Why is your core only so little worse than Intel? Executives don't understand this, but yeah, it's because of this renormalization. You're not running at 3.2 gigahertz. You're not having 128 threads, etc. But we're proud. We're obviously proud of the result. Again, I want to. Okay, and where does this core go? This is a kind of high level, absolutely not good enough to teach the subject block diagram of a NAND controller. In general, if you wanted to teach it in 1 minute, NAND controller or SoC for SSDs is a device that would have two subsystems. There is a front-end subsystem that needs to expose itself as some kind of memory map registers to the host, so that host can program this register with some kind of I/O commands that come from the block I/O. The front end of the SoC needs to understand those commands, like NVMe commands, needs to parse them and understand is host trying to read, write, or maybe do something special. Then there is an internal link to the what's called south end. And the south end contains another kind of subsystem that is talking to the NAND channels, meaning it's taking one host block I/O and it's usually breaking them with some kind of reasonable schema, like 4K into 8 times 512, and it's talking to the NAND channels and is using error correction code engine. So when it writes, it appends ECC. When it reads, it uses ECC to decode to validate that you, as a lucky customer of a USB or HDD, you never really have bad data. So on that south end, that's the processor that we are targeting with RISC-V, and this will be at least for WD. This will be a first RISC-V based SoC for NAND controller applications. Advantages. Full advantage of the open source software ecosystem. We see that as a major thing, because even if somebody in a company is not happy with too much power or too little performance, there is going to be a multitude of RISC-V cores to come. If you have a tool chain, you can actually take advantage of that ecosystem, and that's awesome. Instruction optimization for NAND media handling, that's another great thing. Usually the NAND company like us, they don't want to talk about that part too much, about what's really happening with NAND channels, so you can keep that in-house. And then freedom of power and performance optimization for any application. You can go, like these kinds of architectures, they will go into a big enterprise SSD. It's a 25-watt super optimized beast capable of running at 4 to 8 gigabytes per second, having up to 16 terabytes of storage and whatnot. Or You may have a micro SD card in your phone that needs to have this little piece of silicon that comes with the NAND all packaged carefully together in a tiny little card that's supposed to be cheap because nobody wants to pay their micro SD card a lot of money. And it's very reliable because customers expect when they store photos that the data is reliably stored. So the gamut of power performance is huge. And as our CTO said, he really, when he said it, he meant it, and what he meant we are doing. We really want to take advantage of the number of cores that we are shipping and take a part of the RISC-V movement and start shipping some RISC-V cores. And there's a lot of cores that we ship, so opportunity is very big. Okay, and the second part of my talk is about RISC-V open architecture data center CPU, which is all about open interfaces, and which is actually the primary reason how I got attracted to RISC-V. I met with Professor Krste, with Professor Boro Nikolic from Berkeley. I had a summer intern in my team learn about RISC-V, and at the time, what I was trying to figure out, my team in research has built a sort of a working FPGA prototype back then using Rapid I/O of the cache coherent memory appliance. We wanted to kind of have a appliance that you can hook up to some kind of a cluster and have this memory kind of show up to all the processors in a cache coherent way, so software doesn't have to do any kind of special things. The things just work, and then you accept whatever latencies you may incur in the system. And we kind of had the difficulties with this concept because AGST didn't have a CPU. We could obviously play with little stuff on FPGAs, but we didn't have a CPU kind of product. And then I learned from all the Berkeley guys, hey, there's this RISC-V thing, and I thought, well, this is the answer. If I can have a RISC-V ecosystem develop, and if people start looking at RISC-V seriously, and if they make data center CPUs, there's going to be so many players and so many options that there's going to be opportunity to have interfaces the way you want it or the way your customers want it, but there's going to be no way to kind of prevent what interfaces are available. And this is how we got into RISC-V, and I was talking to people, hey, what about data center CPUs? And they're telling me, no, we're all IoT, what are you talking about? So, but it's moving. And here is the legal approved vision. so sorry, I would just read the words, basically. Multi-threaded, multi-core CPU with a medium performance that would require out-of-order RISC-V core for general purpose OS and software applications. I don't think the world has to go crazy with the performance. It needs to have a good enough performance that can run a normal OS, enumerate peripherals, etc. Need the support for standardized and open interfaces such as JADEC interface for the memory. So one of the interesting things happening in the world of computing is a lot of R&D went into very high density, low latency memories. Intel is at the forefront, Intel Micron at the forefront of that with this thing called Optane. These are the DIMM modules that will carry very high capacities per single slot, allowing you to build computers that have, say, 16 terabyte of main memory that also happens to be persistent. This is a very disruptive thing in computing because it allows, you can keep the same model as we have today, but you can actually even redesign the OS to take advantage of persistent memory. And you can imagine you can get this compute that doesn't have page faults anymore. And this means that kind of the bottom worst latency you can incur in some kind of compute becomes like this 100 nanoseconds. But there is never any more multi-microseconds, page faults, switching the context in the core, waiting for the I/O device to come back, incurring latency because again you're switching context, etc. So So NVDMP is the standard that we've developed in JEDEC with many other memory companies. And we like RISC-V future processors to support it. Then support for high bandwidth and low latency accelerator interfaces. So this is something that's interesting because of machine learning. So the important thing, if you look at how is compute changing in the data center, more and more algorithms that are actually interesting, that are doing interesting things or generating revenue, are employing different machine learning methods. Neural networks being most popular, but many others, like SVM, K-means, they're all very compute intensive. They all kind of boil down to fairly complex solvers. Different kind of accelerators, both for learning or for inference, that have different performance power requirements are being developed. And they all like to have a high bandwidth and low latency interface to the CPU, obviously, so they can get data, so they can share data. Maybe they want to have a cache coherent interface so that there's no need to do DMA twice. These are very kind of interesting and powerful things that now we can explore if we have the fully open architecture. And this last thing that was kind of dear to me from the get-go is support for standardized memory protocol fabric. So this is basically trying to create symmetric multiprocessing for the masses. This is an attempt to create an SMP protocols and hardware that can be shared between the academia and industry that can really be, that we want to become a standard. I'll have a chart to talk about it, but its essence is using a tie-link cache coherence protocol that has to undergo some changes probably to make it more robust. But you basically, you can pack it into a L1 frames of Ethernet. And then there's a lot of new upcoming technologies with programmable networking switches that can be actually used to switch these packets on a network with surprisingly low latency, and I'll show some results. And this gives you a coherent scale-out. So this gives you an architecture where you can have heterogeneous compute. You can basically have two processors from two different groups share memory. And you can have accelerators that can share memory. You can have memory appliances that you can add to the system. So it's a very interesting thing. This has not been standardized before. So this is something genuinely interesting from standardization and openness perspective. What is a memory fabric? 6 or 7 minutes left. That's not enough. All right, no problem. So I think you guys know this. If you want to use some kind of memory fabrics, there's like more than one way how you can do this. The most standard thing is to have a page fault trap that has some kind of remote DMA. You can use RDMA-enabled NICs like Mellanox and InfiniBand stuff. And typically, you incur some context switches and software overhead, but in AGST, we demoed openly and published papers on sort of kind of 2 microsecond memories in a cluster. You can have a global address translation management in software, which enables load and store across this global memory fabric, no coherence. So this is something that exists in the standard called Gen Z. But you need to write a lot of new software. Or you can have a coherence protocol scale out, which is the oldest one from the books. It's a kind of a classic SMP. So that's what we are talking about here. I don't have enough time to talk about RDMA, but we did this very seriously in AGST, and we were able to build these kind of nice demos using Mellanox hardware and our own phase change memory PCI Express cards. We've been able to use RDMA to get sort of a 2 microsecond, you can see it on this chart. Whether we build these remote memories with DRAM or with PCM, we were getting kind of between 1.8 to 2 microsecond latency. Not bad, not quite memory just yet in terms of, in terms of the actual latency. So if we would, try to build an SMP system, we would need Ethernet IP on each SoC, and we would need tie-link messages being packed into L1 frames. So we are kind of working out, how to actually do that. And then we would need a programmable P4 switch. Originally, we played with FPGA chips. Now there are commercial parts. There's a great company called Barefoot Networks that actually tape out the chip that's affordable. The systems are affordable even for academia. They're not cheap. They go into multi-thousands of dollars, but they're not tens of thousands or hundreds of thousands. They're like thousands of dollars. So they're affordable. So the whole thing with FPGAs and P4 switches can actually be created and shared and potentially improved. The latency requirements, we did kind of a lot of measurements to try to understand what is and this is an interesting topic on its own. Like I would like to have a time to write a paper on this. How many nanoseconds you need on a memory to call it a memory. The reason for it is that 3 microsecond memory is not good enough memory today because you can build a block device at the 1 microsecond range, kind of. So for something to be a memory, it really needs to break the microsecond barrier. And then we did a lot of studies by intentionally slowing down the DRAM to figure out what's acceptable. So yeah, maybe 500 nanoseconds for a lot of useful benchmarks is kind of acceptable. This study was kind of spec-int benchmark centric, but. You may ask a very reasonable question. I would expect, I included this chart. If somebody asks, hey, what kind of latency you expect if you are switching these L1 frames? Well, we are measuring in the lab, we are getting about 432 nanoseconds, for the kind of full loop pass. So we think even with this prototype hardware that doesn't use a hardened silicon, we can get something that's actually meeting our requirements for sub-millisecond memory. And obviously, if somebody goes and builds something dedicated, it can be made faster. I'll skip for this. So yeah, in general, the requirements for the and I have a talk earlier this year in SNIA where I just kind of focus on these latency requirements. So you should be able to find it on YouTube if you look SNIA and Bandic. But I kind of explained, if I'm trying to build a very large cluster, what kind of latencies I need from the memory and what kind of latencies I need from the switches so that I scale out to many petabytes or potentially going to exabyte to keep things in memory and not something horribly, horribly slow that will kill all the speeds of all the programs. And the latencies need to be in 100 nanosecond range in order for this thing to work. So maybe my Barefoot Network switch is not exactly where I need it to be, but it's very close, actually. For programmable hardware, it's darn close, right? We wish FPGAs could run at 1/4 speed of real CPU. So, this is a little bit about the MP fabrik memory-centric architecture. We want routable and switchable fabric. We are taking advantage of 25 gigabit per second IP. And it's nice, it has a clear roadmap to at least 56 gigabit with PAM4. What's actually being done, we are replacing L2 Ethernet with tiling on top of A02.3L1. So you can use the standard Ethernet IPs on the SoC. You obviously need some hardware that will actually do the packing. And then the P4 programmable switches are actually allowing you, to parse the packets and to understand how to do the routing. So this is kind of a cool way to do that. We have been using for P4 programmable switch. We have been using Barefoot Networks, and yeah, it's a kind of nice chip. It's available, so you can Google it. It has amazing bandwidth, like 6 terabit per second. And the platform that we are envisioning is kind of shown here. It's based on a Barefoot Network switch and allows you to plug in many different CPU or memory cards. Cards that are heavy on compute, cards that are heavy on memory, and accelerators as well. In terms of what we are planning to open source, subject to internal approvals, we have a production-grade instruction set simulator that has been used in the development of the core. We are planning to contribute the RTL of this two-way 9-stage pipeline. And I think this is kind of targeting December, RISC-V Summit for Santa Clara. where we would announce it, have a name, have the repository so that you can check it out. Longer term, we definitely want to open source the firmware development toolchain. And finally, a lot of things about MP Fabrik, like the spec on how we would pack tiling into the L1 frames, and then the actual P4 language implementation that runs on a programmable switch, and the board designs for which I showed the block, just like a high-level diagrams. And yeah, we want to accelerate the RISC-V ecosystem. You guys know that I can go through this quickly, and that's the end of that would be the end of my talk. Thank you.
Probably have time for one or two questions. Mark, if you wanted to come up and get something set up. Yeah, questions.
Hold on.
Sorry, Julian, I thought, yeah. Sorry for going over time.
What core did the RISC-V end up replacing?
Say again?
What core did the RISC-V end up replacing in the systems that you're
A commercial core.
Can you comment how the fabric?
You have me on camera.
Can you comment how the fabric you were just talking about compares to, for example, Gen Z or some of the other upcoming proposed standards?
Yeah. So my group is a very strong proponent on any kind of memory scale-out fabric. The difference between, I would say, MP Fabrik, we're kind of going old style. So basically it's a cache coherence protocol that runs on a cluster, right? And we're trying to build a demo with 2 RISC-V boards where we'll boot Linux and see all the cores, right? And go through the switch. Gen Z is powerful, but it has a lot of pre-existing IP, and it's still waiting for the CPU vendor to support it. So for RISC-V community, it would be a bigger, it would be bigger hill to climb. So I think something like MP Fabrik is much better as the first step, have everything in open. But it doesn't preclude if somebody develops a good data center processor, they can go with Gen Z. And I think Gen Z is potentially more powerful architecture if you really want to go into exabyte, but you're really going to need a lot of software too. So I wanted for my first project to find a passage that will not require me starting a massive software, open source software, people to work on 1 million lines of code just yet. Yes, but yeah, we like Gen Z.